ions stick together through electrostatic forces. That's ionic compounds. That's pretty much all we have to say. We'll talk a little bit about how we can make some conclusions about strength of ionic interactions in a little bit. But basically, it's using Coulomb's law, which is from physics, just saying that charges attract each other. And that's the law that calculates how strongly they attract each other. We won't be doing those calculations here, but it's the same thing as if you just had some point charges. What's more interesting to us for this part is looking at what we call covalent bonding, which we think of as sharing electrons. But it's actually a little bit simpler than that. What this is a picture of is two hydrogen atoms at different distances from each other. So the x-axis is internuclear distance, meaning how far are these two things apart from each other, two hydrogen atoms. At the far left, they would be on top of each other. So the internuclear distance is 0. It means they're on top of each other. The far right means they're not interacting at all, totally separate from each other. The y-axis is potential energy. So the lower on the y-axis, the more stable. The higher on the y-axis, the less stable. If you see over at this extreme, over on the right, you have infinitely separated atoms. So if the atoms are separate, the difference in potential energy is 0 because they're just separate. They don't affect each other at all. So that's like our baseline. That's our starting point. Just two atoms that have nothing to do with each other. As they get closer and closer, we can see that the energy goes down. And then it gets to a certain minimum, and then it shoots way up. Why do you think it shoots way up as we go to the far left? What's happening like in this situation over here? Take a look at that figure.
They're passing each other.
They're what?
Passing each other?
Yeah, essentially they're on top of each other. Nuclei are going to repel each other because they're positively charged and they have mass. You can't put two masses in the same place. Two masses can't occupy the same space. So as those nuclei get closer and closer together, the energy goes up to infinity because they're just starting to repel each other, until you're trying to get them to take up the same space, and that's certainly not going to happen. So that's why the energy shoots up all the way to the left. What this tells us then is that there is some optimal distance when those two hydrogen atoms are close enough together, but not too close. That stabilizes the whole thing, stabilizes both atoms together. And that's why there's a big dip. So that's what we call, that's really all a covalent bond is two nuclei being close enough for the optimal energy. And that's what we call a bond. In the case of hydrogen, it's at 74 picometers, which is 0.74 angstroms. And so the energy goes down by about minus 432 kilojoules per mole, which is how much energy is released when you form a hydrogen molecule. All right. That's what we call covalent bonding. The reason for that, we'll get into in a minute, but the reason for that drop in energy is that at this particular distance, the valence shells of the two atoms are overlapping. And you can kind of see that from the picture. Once they get close enough, the valence shells overlap so that the electrons can actually be found in both atoms instead of in just one. And that's the stabilizing interaction that we call a covalent bond. So covalent, meaning co meaning together, valent like the valence shell. So covalent. Usually, though, the situation looks something more like this. So here's our two atoms. This is now H and F. And this is a plot of electron density, meaning how much more likely is the electron to be found in one place rather than the other. The darker red, the electron is more likely to be over in that area. So in this example, rather than the two atoms sharing the electrons equally, you have unequal sharing, meaning the electrons are pulled more toward the fluorine and away from the hydrogen. And that's what we call polar covalent bonding. So we can have now three situations. We can have ionic bonding, which is not even really bonding per se, but just two separate ions that attract each other. You can have pure covalent bonding, where two atoms share their electrons equally, and then you can have polar covalent bonding where there's unequal sharing of electrons. The way we express this is through these little symbols. This is a Greek lowercase letter delta. We say delta plus for where it's more positive and delta minus for where it's more negative. This is because the electron is pulled more toward the fluorine. Now, if it were just plus, the reason we don't just say plus and minus is because that implies a full charge like an ion. So an ion would get a full plus or a full minus. Because this is part of a covalent bond, we have a partial positive or a partial negative. So these things here are partial charges. And the way you draw that is you kind of start at the top, right around like that, and that's a lowercase delta. Some people call it that snake thing, but you can just call it delta. All right. The property that causes this is something called electronegativity, and this is this ability to attract shared electrons to itself. So it's not saying that something with a high electronegativity can simply reach out and grab electrons and become negatively charged. It says within a bond, an electron that is, or an atom that is more electronegative will tend to attract those shared electrons more to itself and not share them equally. So we can look at electronegativities on a table like this. This is from the book. Kind of gives you a graph of them. And the higher the electronegativity, the more likely this is to happen. So if we look at hydrogen, for instance, right over here, a hydrogen-hydrogen molecule has no difference in electronegativity. You've got hydrogen on one side at 2.1, hydrogen on the other side at 2.1. The difference is 0, so we would expect perfectly equal sharing. But if we look at hydrogen to fluorine, I don't know if you can read those numbers, but hydrogen is 2.1, fluorine is 4.0. So that's a difference in 1.9. That's a pretty large electronegativity difference. So that tells us that the more electronegative fluorine will pull those electrons toward itself away from the hydrogen. And that's how we can predict whether a bond will be polar or not. Now, you don't need to memorize these numbers because we can usually figure this out looking at some general trends. So do you see any kind of general trend in this graph? Remember we talked about periodic trends is like if you move one way or the other. Do you see anything that pops out at you as a trend going in one direction or the other? Yeah. Yeah, it seems like to the right and up, it roughly goes from lower to higher electronegativity. Does everybody see that? Another way to think about this, it says it right here, is that fluorine is the most electronegative element, and so everything else kind of trends toward fluorine, roughly. Now, just like anything else, it's not perfect. There's some humps and some ups and downs, and but generally, with the atoms we're going to care about, that will be a good enough approximation to get us where we need to be. Look at the second row here, for instance, B, C, N, O, F. They go up by 0.5 as you step to the right. So you can reliably say, all right, anything to the right is going to be more electronegative than anything to the left. And that means that if you have a bond between something in the right and something on the left, you would expect that to be a polar bond with whichever element closest to fluorine pulling the electrons. Same thing going up and down the groups this way. You can see a pretty big jump going from that second row to the third row, and then the difference changes significantly. But if you could said something like, well, between a silicon and an oxygen, you would expect to have a pretty strong difference in electronegativity. Going the other way, that's a lot harder to judge. So you can't always judge it based on this trend. Sometimes you need to pull out a chart and look up the numbers. But usually at a first approximation, we can figure it out just by looking at those trends. So just by remembering these trends, we don't have to remember all the numbers. The only thing that I would say, and some books do this differently, remember hydrogen is a little bit weird because it has one electron, so it starts way up at the top, but it's really not a metal, it's a non-metal. It really belongs over in the non-metals. And the electronegativity kind of points to that as well. So if we think about the trends, hydrogen should really kind of fit over here somewhere. And sometimes there's some alternative periodic tables you can look up that show that. All right, so for a rough approximation, we can put things in these different buckets, and we can call them covalent, polar covalent, or ionic based on their electronegativity difference. Now that is an approximation. That's like an arbitrary number. Somebody said, okay, we're going to stop it at 0.4. Anything less than 0.4, we're going to call nonpolar. Anything greater than 0.4, we're going to call polar. And that is pretty useful in terms of thinking about intermolecular forces, some of the stuff we're going to get into. It's not always right. So you shouldn't think of this as like an absolute, especially with ionic. And we're going to look at this, I think, in a minute, right? Go look at it down here. We'll just skip and do this part first. The reason it doesn't work with ionic is that something being ionic has an actual meaning. If something is made up of charges, you can actually tell that experimentally. How can you tell if something is made up of ions experimentally? Yeah. What should it be able to do that non-ionic compounds would not be able to do? What?
Attract and repel.
Attract and repel. Yeah, and the way that that's tested is usually through electrical currents. So an ionic compound should be able to carry an electrical current, whereas a covalent compound would not. It would insulate. And so if we look at the conductivity of these materials, usually we melt. The way you test this is usually you melt it, and then you test the conductivity across the molten solid or the molten liquid. Then you can tell if it's an ion or not. And you can set up this kind of a graph which plots the percent ionic character, which is an experimental designation of how ionic it is, versus the electronegativity difference. So the table that we just looked at tells us the greater the electronegativity difference, the more ionic it should be. This says, well, is that right or not? And if you have done some graphing type stuff before, you can see that this roughly works, right? It's approximately correlated into a line, so that the more electronegativity difference, the bigger the difference, the bigger the ionic character. But you can also see that there's plenty of things that don't quite fit in that line. It's not a perfect correlation. So there's materials like HF that have a pretty large electronegativity difference, but actually are not really ionic. And then there are things like some of these salts, like cesium iodide, which actually has a lower electronegativity difference than HF, but is really ionic. So this is just an illustration of that idea that this, we'll go back to that before we get into ions. This idea that to classify things as ionic or covalent based on their electronegativity difference is kind of an approximation and not really like a reflection of true reality all the time. All right. What we're going to want to do then is be able to figure out if a bond is going to be polar or not. Ideally without looking at the chart, but sometimes we're going to have to go look at the chart and figure it out. So without going back to the notes or to the chart, see if you can order those 5 bonds according to polarity, which would be, let's say, least to most. So least polar to most polar. And you're going to be guessing this. This is going to be kind of a best guess scenario. And try to figure out how certain you are about different rankings. Like I would say you should pretty easily be able to get the ends, the most and the least polar. And those middle ones, you're going to do your best guess on. So everybody try to rank those, write down a ranking as best you can. And then maybe put a star next to the ones that you're pretty sure about, and maybe a question mark by the ones that you're not quite sure, without looking up any numbers. And we'll go back and look up the numbers and see how we did. All right, everybody got some sort of rankings? Give it another minute to get them down. All right. So who's got one they're pretty sure about, either on the low end or on the high end of the spectrum here? You could say, I'm pretty sure this one is either the least polar or the most polar. Right, feel good about it? Yeah, go ahead.
Fluorine and hydrogen have the most polar.
Fluorine and hydrogen the most polar. How'd you come to that conclusion? Yeah, right. So right. So whatever hydrogen is, all of these things have hydrogen. So hydrogen with the most electronegative one is going to be for sure the most polar. Did other people find that too? Mostly? Okay, good. So we'll put that over on this end of the spectrum. All right. What about the other end? Anybody find pretty sure about which one is going to be the least polar? Yeah. Yeah, hydrogen's got to be the least polar because it's 0. You know there can't be any polarity when you've got two of the same thing. There's not going to be, the electrons are not going to be going to one side or the other. All right, so now we've got 3 more to try to figure out. So 3 more spots to figure out. Anybody feel good about another one that fits in there somewhere? What do you think? At this point, we're guessing a little bit, right? We got our extremes. Now we have to make some judgments. So what kind of judgment do you want to make? Yeah.
OH is on the right.
Sure. So OH, we're going to put here. Why?
Because I think it's greater left before it goes greater down.
Yeah. Well, the other way. Yeah.
Yeah.
It gets, yes, it goes smaller as you go down faster. Right. So we've got 2, this is how I would look at this. You've got 2 atoms that are right next to fluorine. You've got oxygen and chlorine. So we're trying to judge which one of those is going to be more electronegative. In this case, it's oxygen, and that's correct. You wouldn't be wrong. I mean, you'd be wrong, but it wouldn't be a bad guess to say chlorine fits there also, because that's also right next to fluorine. But in this case, oxygen is probably the better option. All right, so then assuming we put oxygen there, can you order the chlorine and the sulfur? Which one would be more polar, chlorine or sulfur?
Chlorine.
Chlorine, because we know the trend is generally to the right. Okay, so this is going to be our guess, and we're pretty sure about this one, and pretty sure about this one, and maybe questioning the other 3 we could look up. All right, let's look up those numbers back on our table. So oxygen's 3.5, chlorine's 3.0, and sulfur's 2.5. So the difference in electronegativity, let's write it for all of them. We'll call it the delta En. 0 for here. Remember, hydrogen is, I think, 2.1, right? Yeah, 2.1. So this one, the difference is 1.9. So 3.5 minus 2.1, that's going to be 1.4. 3.0 minus 2.1, that's 0.9. And then 2.5 minus 2.1 is 0.4. So that's the correct ranking. So really, a sulfur hydrogen bond is also really a nonpolar interaction. There's not a large, that electronegativity difference of less than 0.5. We usually say that's not really polar, not polar. So these are kind of the polar bonds here, and these are the nonpolar bonds here. Okay. So you should be able to think about polarity in this way. And if you do enough practice problems, you shouldn't really have to memorize any numbers to be able to do these kinds of things. I wouldn't ask you some crazy thing like, what's the polarity of a PS bond or something without giving you numbers. But you should be able to tell that probably that sulfur is going to be a little bit more electronegative than the phosphorus. All right. We're going to put these together then and talk about the polarity of a whole molecule, which is called the dipole moment. So far we talked about bond polarity, whether a particular bond is polar or nonpolar. We can add the polar bonds together and figure out if an entire molecule is going to be polar or nonpolar. In order to do that, we need to know the shape of the molecule. And probably tomorrow we'll get into how to determine the shapes of molecules. But for now, let's look at water. Anybody know the shape of water? Yeah, it's kind of like a triangle bent thing. We'll get into how we know that later. Well, we can draw a water molecule like this. Now, if we want to know whether or not water is a polar molecule, we first have to look at the bonds that water is made out of and figure out if they're polar. But that's not the end of the answer. So in this case, are water's bonds polar? Is an OH bond polar? It is, right? Everybody agrees? Okay. So that's the first step. Figure out if the bonds are polar. Second step, add the polar vectors together, the polarity vectors together, known as the dipole moments, and figure out if the overall molecule is polar. So let me show you how to do that. For each bond in the molecule, you figure out where the electrons are going. So we're just going to look at one particular OH bond. We'll look at the one over on the right. Where are the electrons going? Are they drawn more toward the oxygen or toward the hydrogen? If that's a polar bond, are the electrons pulled more toward the oxygen or toward the hydrogen?
Oxygen.
Toward the oxygen. How do you know that?
Because it has a stronger.
Right.
Yeah.
Higher electronegativity. Yeah, the stronger pull. So that means that we're going to have a partial negative charge on the oxygen. It's going to be partially negative because the electrons are being attracted to that spot. And they're being pulled away from the hydrogen. So the hydrogen is going to be partially positive. All right. The other way that we can express that then is through drawing a vector, because really what this is a vector quantity. Has anybody ever dealt with vectors in physics before? So you sort of know what I'm talking about. A vector is a quantity that has both a magnitude and a direction. So it has a size, but it also has a direction. And that's really what a bond dipole is. It's not only how much of a difference is there, it's where is that difference manifested? What direction are the electrons going? So we draw that as a kind of a vector with a little plus sign on the end. If we know that the electrons are going from the hydrogen to the oxygen, we make a little plus on the tail of the vector and point toward the oxygen to say, here's where the electrons are being pulled to. And then since the other side is the exact same, we have the same thing on this side. All right, so we've got two vectors indicating the dipole moments on those bonds. Okay. So then, to figure out the polarity of the entire molecule, we add the vectors together. Does anybody know how you add vectors? Have you ever done that in physics? Maybe a long time ago. You just kind of, we're not going to add them like mathematically. We're just going to add them qualitatively, like descriptively. So what we're going to do is we're going to approximate the size of the vectors, and we're going to stick them on each other, kind of like following a path. And we're going to figure out the sum of those things. So the vector on the left goes like this. that we drew. The vector on the right, we're going to put going the other way, and they should be about the same size because those are both OH bonds. So I didn't really draw that the same size. Be like that? Does that look about the same size? It's not quite the right angle. Let me try that again. You know what? I got technology. I'll just use my technology. See this? Stick it on the end. Okay. So there's our two vectors. So that means that the overall dipole moment, the sum of the two vectors, is kind of like where would you end up if you went on this path formed by all the vectors. And in this case, it's like this. So that's the overall dipole moment. All right, there's another way to figure this out too. So if you have a complicated molecule, you can always do this. You can add up all the bond vectors and figure out the overall dipole moment, the exact direction, and all that. The other way to do it is to think about what it says here. A polar molecule is one that has a center of positive charge and a center of negative charge. So the other way to look at this is to take the water molecule and recognize that if we draw the polarities of the bonds on both sides, what we've really done is we've separated that water molecule into two sections. And we can say this part is the negative part and this part is the positive part. Do you see how the positive charge is localized around the bottom of the molecule and the negative charge is localized around the top of the molecule? So that's another way to indicate that this molecule is going to be polar. If we didn't see that, and we'll look at some examples where we don't see that in a minute, then we would know that the overall molecule is nonpolar, even if it's made up of polar bonds. We have to also remember that first picture. So covalent bonds, remember, are these two atoms kind of mashing their electron clouds together. We draw them with these lines. These lines indicate specifically two shared electrons between two atoms. But in real molecule world, there's no lines. So really a water molecule might look something like this. You might have seen these kinds of models before, what we call a space-filling model. Something like that, where you kind of have them mashed together. And here are the hydrogens, and here are the oxygens. That's more reflective of what that would really be like. So if you imagine the hydrogens kind of having, not being ions, but having some general positiveness around them because they're missing, their electrons are being pulled toward the oxygen, which is having some negative up here, you can pretty clearly see that there's some positive hydrogen stuff down on the bottom and there's some negative oxygen stuff up on the top. So that's what we call a polar molecule. Polar and dipolar mean the same thing. Dipolar means to have two poles. You can't have just one. You can't have a molecule that just has a positive side and no negative side. So yeah, anything that's polar is going to necessarily be dipolar. That just means separated into positive and negative. So we'll look at some other molecules to see this as well. I want to jump down here to look at CO2 because this is an interesting one. Does anybody know the structure of CO2? Most people need water. Anybody know CO2? In the second half of this chapter, we'll talk about how to draw all these structures. But CO2 has a carbon atom in the middle and two double bonded oxygens on one side or the other. And it's a linear shape. So instead of being bent, it's straight across. We can do the same kind of bond vector analysis for carbon dioxide. So is a carbon-oxygen bond polar or nonpolar? Wait, we should check, right? So let's look at the periodic table. Would you expect a difference in electronegativity between carbon and oxygen, or would you expect them to be roughly the same? What do you think? What does the trend tell us? this way and up. So oxygen's to the right of carbon, so we would expect that to be a difference. So we would expect this to be polar. And if we go back and look at our numbers, I think the difference in those two is like 1, a difference of electronegativity of 1. So that would be a polar bond. That means that electrons are going to be pulled toward the oxygen and away from the carbon, toward the oxygen and away from the carbon on both sides. All right. Now let's look at those bond vectors and see what our analysis would look like. So we'd have one going in this direction, and then one of equal magnitude going in this direction. What is the sum of those two vectors? It's 0. So if you go a certain amount in this direction, and then you go the same amount in this direction, you're back where you started. So those two, the sum of those two vectors is 0. That means that the carbon dioxide molecule is not polar, has no net dipole moment. That term dipole moment is the kind of mathematical term for the overall bond, or the overall dipole vector of the molecule. So the overall dipole moment in carbon dioxide is 0. That means carbon dioxide is a non-polar molecule, even though it is made up of polar bonds. We can see that carbon dioxide without doing the bond vectors also in that other way of looking. Is there an area of positive charge on one side of the molecule, negative charge on the other side of the molecule? There really isn't. The positive charge is concentrated in the middle. The negative charge is on either side, so kind of surrounding the whole molecule. So you don't see a positive side and a negative side with carbon dioxide. You just see the same all around the outside. So this makes it a non-polar overall molecule. All right. So now I want you to try this with these 5 molecules. Now, I know we haven't talked about how to make the shapes of the molecules, but they're described here for those that are important. If it's not described, then you have to use your best guess and try to figure out what the shape is going to be based on what you already know. But see if you can draw these 5 molecules, decide if the bonds in those molecules are polar or not, and then you know there's some guessing involved here, and then determine if the overall molecule is going to be polar. All right, so give that a try for those 5. About 5 minutes.
I need to know the, I don't know how you're seeing about the numbers. I know the numbers for this one, right? So I need to know.
Yeah, I mean, if you want to know, like, for sure what it is, the numbers. So there's a bit of a guess here. Do you think that it's likely that there would be that, or do you think it's not based on the track?
So if we do HCF minus hydrogen, you know how we have those numbers? So do we,
For the electronegativity?
yeah.
Yeah, if you're looking up the electronegativity of performance and tracks, if you don't have those numbers, then you just have to make a judgment
And
on
then
whether or not you
you
think
said
it's
if it was less than 0.5, it would be not polar.
right. All right, got some ideas about these? So again, I'm not asking you to look up the numbers. You're not going to have those numbers with you for quizzes and exams. You're going to be asked to kind of use your chemical knowledge and background and the ideas of these trends to figure out what you can figure out. The more experience you have with this, the better. Whoops. Oh, where do we go? There we are. How many, let's first talk about how many of these 5 did you think were polar? How many people thought one of them was polar? 2, 3, 4. They were all polar? None of them were polar? I didn't say none. Who thought 0 was polar? All right, so just no one's voting. All right, let's look at them then. Were there any of these that you're pretty sure were either polar or non-polar? Because I think there were some that were a little clearer than others. What were you? You're nodding your head. What were you pretty sure about? HCl, you said was polar. Okay. How do you figure? Right. Chlorine's a bit more electronegative than hydrogen. Being over to the right. Yes, it's down a row, so it could be close, but it's probably a good guess to think that's polar. And you can remember, you don't have to answer these questions completely separate from all of your own experience. You should know, based on your chemistry background, that some things about HCl, like that it dissolves in water, that kind of thing, and maybe you can help. That can help you make that determination that this is probably a polar thing. Okay, good. Other ones that you're pretty sure of.
SO3.
SO3 is what?
Polar.
Is polar? All right, so how do you figure that?
S is below O.
S is below O, so we know that an SO bond is going to be polar, right? All right, so let's look at the structure of SO3. Remember, we didn't talk about how to build these yet, but it does tell you it's a planar molecule, meaning flat, with oxygen atoms spaced evenly around the central sulfur atom. So that would be something like this. Sorry. And actually we often draw this, even though it's not necessarily correct, we often draw this with double bonds. We'll talk later in the chapter about why that may be correct or not. All right, so then we've got sulfur, oxygen, clearly polar bond vectors here, here, and here. If we add up all those vectors, what do we get?
0.
Yeah, you get 0. Let me show you how that works. So we'll take this one, and then add this one, and then add this one, and you're back to where you started. So this is overall nonpolar. You're right that it's made from polar bonds, but this was kind of the tricky one. So no net dipole moment. Dipole moment 0. Another way to see that here is kind of like what we talked about before, that there would be no way to say this side of the molecule is more polar than this is more negative, and this side of the molecule is more positive. That in this case, it's totally symmetric. Whenever you see these very symmetric molecules, even if they're all made of polar bonds, there's probably a good chance that it's overall not polar, because the symmetry will cause all the bond vectors to cancel each other out. All right, so that leaves 3 more. What do you think about those? Do we feel good about 1 or 2 or 3 of those other ones? Maybe or not. What about Cl2? That should be an easy one. Is that polar or nonpolar? That's got to be nonpolar. If you've got, just like H2, if you've got the same atom on both sides of the bond, can't have any difference in electronegativity, definitely nonpolar. All right, so the tougher ones to look at are going to be CH4 and H2S. Those are ones where it's not really an obvious, whether one is higher in electronegativity than the other, and we should look at the table. So how many people said CH4 is polar? I'm not going to make fun of you if you got it wrong. I'm just saying, you know. How many said polar? Nobody. How many said nonpolar? Okay, so people, do you look it up or you just figured?
I just kind of like figured that the hydrogens would be equally spread out, and then those vectors.
So even if there were even if they were polar, they would be evenly spaced out and cancel each other out, right? And that's true for CH4. But let's look back up the numbers. Actually, the difference in electronegativity between hydrogen and carbon is so small that those are nonpolar bonds anyway. So hydrocarbons, which are molecules made from carbon and hydrogen, are generally nonpolar. So for both of those reasons, then, CH4 would be nonpolar. But even if it were not symmetric in that way, it would still be nonpolar because there's not that big of a difference. What about H2S? How many people thought H2S was polar? And nonpolar? A couple people? Most people, no idea, maybe. Just put your hand up with some other people. Give it a try. Thanks for voting anyway. But it's actually polar. You're switching them? Yeah, this is another tough one because, first of all, what should the shape of H2S be, do you think? Do you think it would be linear straight across, or do you think it would be bent? Why? Just guess. Okay. Yeah, and like I said, we haven't talked about how we figure that out yet. But actually, one thing we can use is periodic trends. Sulfur is right underneath oxygen. We know that things in the same column have the same number of valence electrons, so they generally have the same types of bonding properties. So if H2O is bent, then we would expect H2S should also be bent, as a approximation anyway. That said, though, it still doesn't matter because the difference in electronegativity between sulfur and hydrogen is also really too small to be polar. So that would also be non-polar, even though it does have a slight bend to it. All right. All right, so now let's move away from the covalent compounds for a little bit and just talk a little bit about ions. So we know some things about ionic compounds already because from what we did in the naming in the previous chapter, so I'm going to skip a lot of this stuff. What we do want to look at is the electron configurations of ions, and we talked about this before. Ions will arrange themselves as to minimize the or to maximize the electrostatic attractions. So they're going to arrange themselves kind of packed as closely as possible. You're not going to see ionic compounds having these kind of different shapes the way molecular compounds would. So they kind of just all pack together. And there are different shapes, different structures of ionic compounds. If we have time at the end of the semester, we'll get into some of those structures. But we don't draw them in the same way. So we shouldn't ever draw lines connecting ionic compounds or ions as though we were building molecules. We don't want to see like Na and then a line and then Cl, because that line specifically means sharing electrons. We don't see that with ions. So let's review our electron configurations again. What's the electron configuration of calcium? Neutral calcium? Yeah. Argon, 4s2. And what about oxygen? Yeah, go on. Helium. Yep. Yep. 2s2pp4. Good. All right, so those are our electron configurations. So now let's look at the ionic configurations. If calcium loses 2 electrons and oxygen gains 2 electrons, how do we change the electron configuration for calcium?
Calcium would just be argon.
Right, we just lose those 4s2, so we could do argon, or we could jump down and make that like this to show that there's 6 valence or 8 valence electrons there. Either one of those is fine. And then what about oxygen 2 minus? So if we add 2 electrons to oxygen, what do we get?
Yeah.
Same thing, right? Well, not the same thing, but we could have 2 different choices there. We could write it like that, showing 2 more electrons going into those p orbitals, or we could just call that neon. All right. We'll talk about these Lewis structures more later in the chapter. I guess we might as well define that here. When ions gain or lose electrons, we can express the valence electrons as little dots. You may have seen this before. So we would draw calcium with 2 dots and oxygen with 6 dots. And then we could talk about as they form ions, we can see pretty clearly based on the octet rule that oxygen wants to get 2 more to fill in those spots. Calcium wants to lose those 2. This is more important with covalent compounds than ionic compounds, so we'll skip that for a second. All right, so some things about sizes. We talked a little bit about ionic size in the previous chapter, but let's look at these 3. For isoelectronic ions, we can predict the trend based on charge. So isoelectronic, iso means same, electronic, electrons, so same number of electrons. If you look at O2 minus, F minus, Na plus, Mg2 plus, Al3 plus, those all have noble gas configuration. Those all have neon configuration. So which one is going to be the biggest of those 5? You remember for the trend for that? Which of those 5 ions is going to be the biggest? Yeah. The oxygen, how do you know? Yeah, so they all have the same number of electrons, but it has the most electrons relative to the size of its nucleus. Right. Oxygen has all of those particles listed there, the ions, have 10 electrons. But oxygen has 8 protons, fluorine has 9 protons, and so on. So if you have extra electrons than protons, that means you're going to be bigger. If you have fewer electrons than protons, that means you get smaller and smaller because of the stronger attraction from the nucleus. So the trend in the way that this is written is going to go larger to smaller. That aluminum 3 plus should be very small relative to oxygen 2 minus. It should go down. That's not an easy comparison when you don't have isoelectronic atoms. So if we said, what's bigger, O2 minus or, I don't know, K plus? Now, yeah, the O2 minus is a little bit bigger, but the K plus is a couple rows down, so that's not really a comparison we can make without going back and looking up some numbers. But when we look at the same number of electrons, just different sizes of nuclei, that we should be able to figure out. All right, so let's try that again. See if you can arrange these 4 in order of decreasing size, and then choose the largest ion in each of those groups. See if you can write down a ranking there. All right, we got a ranking. So how are those hard to arrange in an order of decreasing size? They're sort of already there, right? So it's just as is. We've got, again, a set of isoelectronic ions. So the more negative charge is going to be bigger, more positive charge is going to be smaller. And that's exactly how they're written right there. All right, what about the second one? What's the largest ion among the 5, or the 5, alkali metal ions listed there? Which one's largest?
Cesium.
Cesium. How do you know?
This down on the table.
Yeah, furthest down on the table. So we know that each shell we move out, we get bigger and bigger and bigger. Now, if that said, what's bigger, cesium plus or rubidium neutral atom? That's not an easy distinction to make. But because they all have the same charge, we can use our periodic trends and determine which one's bigger. And what about the second group? Barium, cesium, iodide, and telluride ions. Yeah, it's got to be the same thing. So this is another example. Isoelectronic ions, you're going to pick the one with the largest negative charge. Okay. So the last thing we'll discuss in terms of ions is this idea of lattice energy. Lattice energy is specifically defined as the energy released by the ions when they come together to form a solid. We talked about how ions attract each other. So the lowest possible energy state is for those ions to all be packed close together. If you imagine all the ions being separate and then packed them together, that releases a bunch of energy because it's lower on potential energy. Now there's this whole thing in the book about stepping through how to calculate the lattice energy from all this stuff. We're not going to do that. We want to think about lattice energy descriptively, meaning how do we judge relatively which types of things will have higher or lower lattice energies. When we talk about a higher lattice energy, we're talking about the exothermic lattice energy, that is the magnitude of the lattice energy. So yes, the larger LICL has a more negative lattice energy. Technically on a number line that's lower, but we say that that's a greater lattice energy in absolute value. So it's more exothermic. Smaller ions generally have larger lattice energies than larger ions, meaning that their crystalline structures are more stable than the others. Why do you think that is? Why should smaller ions have greater lattice energies than larger ions? Ideas? Just guesses, whatever you think. Why should smaller charged particles pack together more strongly than larger charged particles?
The electrons stay closer to the nucleus.
The electrons are closer to the nucleus, and then they're so much smaller. It's really just as simple as packing. If you have a bunch of tiny little spheres, you can pack them a lot more tightly than some giant playground balls or something. They're going to have greater contact between the ions. So the smaller particles, the smaller charged particles will pack together more efficiently than larger charged particles, and that's going to affect the lattice energy. So here you see that in this case, the chloride ions kept the same, and you go from smaller to larger cations, you decrease the lattice energy. And then the other effect on lattice energy is the larger the ionic charges, the larger the lattice energy. And this difference is much bigger than the size difference. So a +1, -1 type of lattice is not going to be as strong as a +2, -2 lattice by a lot. Why do you think that is?
They have stronger connection.
Yeah, the stronger attractions. Coulomb's law just tells us the attraction, and it's dependent on the magnitude of the charge and the distance between the charges. So the closer the charges are together, the stronger the interaction. That's number one. And then the larger the charge, the stronger the interaction. That's number two. So we should be able to judge relative lattice energies based on the charges and then based on the sizes of the ions. All right, so we can do something like this. Arrange these ionic compounds in order of increasing magnitude of lattice energy. Let's see if I can keep that. Yeah, not quite. So we're going to look at these four and judge the size as well as the charge and see if you can put them in order. See if you can come up with an ordering of these four from smallest to greatest magnitude of lattice energy. That is the weakest interactions to strongest interactions. We got it? Think about that. All right, which one of these would be, well, let's think about this differently. In this case, we probably want to break this up into two groups. We said that the magnitude of the charge was more important than the size of the ions. So we've got two of these that should definitely be bigger lattice energy than the other two. But which two should definitely be bigger? We'll talk about the ordering of those two in a second, but which two definitely would be bigger?
CAO and SRO.
Right. We know these two will definitely be bigger than the others because that's 2 plus 2 minus versus 1 plus 1 minus. Within those groups then, what's going to have the greatest lattice energy? Calcium oxide or strontium oxide?
Strontium oxide.
Why?
It's bigger.
Right, but it's the opposite. Right, so you're right that strontium oxide is bigger. Calcium oxide then will have the stronger lattice energy. So calcium oxide should be our greatest magnitude of lattice energy, followed by strontium oxide. And then how do we order the potassium bromide and potassium chloride? Will the bromide be bigger, or bromide have a greater lattice energy, or chloride? Chloride, same reason, right? Smaller. So our lowest magnitude of lattice energy should be the KBr. That means the least negative, then KCl, strontium oxide, and calcium oxide. That should be our basic rankings. That work? Okay. So we talked about this a little bit, this idea of, I don't know why this is later in the notes, it should have been when we talked about the other stuff, but this idea that you have these three situations now that we talked about today. We talked about perfectly polar or non-polar covalent bonds, perfectly covalent or non-polar covalent bonds, polar covalent bonds in the middle, and then ionic bonds. So it's really this continuum. And where we draw these lines to call something non-polar, polar, or ionic is pretty much arbitrary. Right. And then we talked about how we have this. So really a better way to classify something as ionic is not based on its electronegativity difference, but based on experimentally checking whether or not it actually has ions in it. Does it conduct an electric current or not? If it does, we should call that ionic. If it doesn't, we should call that covalent, regardless of what the electronegativity tells us. So the electronegativity may help us predict that, but we should really use the experimental measurements to make that determination. All right, so that's it. Come back at 11, and we'll work on some problems related to this stuff, as well as we should probably look at some of the chapter. Do you still have a thing from chapter 8, a worksheet from chapter 8 from last week? So if you haven't finished that up, you might want to pull that out also. But I'll have new ones for this too.